Now, it turns out that gravity also acts as a centripetal force in many cases, or a force causing circular motion. The orbit of satellites around our planet can be considered an example of circular motion, where the force that the Earth exerts on the satellite is the centripetal force, or the force causing the motion in a circle. And this goes far beyond just our Earth and satellites. The orbital motion of our planets and of our solar system and our galaxy can also be explained by the attractional force of gravity acting between large bodies in space, creating centripetal forces. And so in this case, if I were to draw the force acting on the satellite, I would show it like this, right? This is the force of gravity exerted on the satellite by the Earth. Now, obviously, again, there's that other force that the satellite exerts on the Earth, and these are equal to each other, right? We know that those are equal to each other. But given the extreme difference in their masses, the Earth does not accelerate as a product of this force. So, because I know that gravity can act as the centripetal force in this case, and I can analyze the motion of the satellite, I can say that the net force pointing into this circle, this circular path that the satellite will take as it travels around the Earth, will be equal to the force of gravity exerted on the satellite by the Earth. And so if I were to expand both of these terms, I would say that the mass of the satellite multiplied by that inward acceleration, or the centripetal acceleration of the satellite, will be equal to, again, the force of gravity on the satellite would be the Newton's law of gravitation, the mass of the satellite multiplied by the mass of the planet, in this case it's Earth, but leave it generic, divided by the r squared. And again, this r value, right, is the distance from the center of the Earth to the satellite. I'll show that on my diagram here in yellow. Now, I see that the mass of the satellite actually appears on both sides of this equation, right? The centripetal force and force of gravity both increase as the mass of the satellite increases, but by the same amount. So I can cancel the mass of the satellite in both of these equations. And if I were to expand the acceleration of centripetal, I can show this as the tangential velocity of the satellite squared divided by the radius, which again, this radius is the distance from the center of the circle that the satellite is taking. In other words, it's the same r as the center of the Earth to the satellite. That would be g times the mass of the planet divided by r squared. And since this r is the same, I can multiply both sides by r. This will cancel, and if I multiply this by r, show that here, this will go down to 1. And so the tangential velocity squared of that satellite will be equal to g times the mass of that planet divided by r. And if I were to take the square root of both sides to solve for the tangential velocity, then I would say the tangential velocity of the satellite is equal to big G times the mass of that planet, or celestial body, divided by r, which again is that distance from the center to the satellite. And so what this tells us is that the velocity that a satellite needs to have, in other words, in order to launch a satellite into space, right, into orbit, we need to know what this VT is to be able to do that. And we know that the velocity needed to keep this satellite moving in a circle above the Earth, a certain distance, r is the distance from the center of the Earth. So we, again, if we know the center or the Earth's radius, we can solve for r. If, let's say, the satellite is 300 kilometers or 200 kilometers above the Earth's surface, we can add that to r. This formula allows you to determine what that velocity needs to be to keep a satellite in orbit at a certain altitude, right? Just depending on the mass of the planet and how far away from the planet you want the satellite to orbit. It actually does not depend on the mass of the satellite at all. And so we also see that some interesting takeaways are that if you increase the mass of the planet, you actually need a larger tangential velocity to keep that satellite in motion. So if we were on another planet, like a heavier planet, right, and we were trying to launch a satellite on that planet, you would need to launch it with more velocity to keep it going in a circle. If you also were to increase r, so either the radius of the planet itself or how high above that planet you want that satellite to orbit, we actually would then decrease the necessary tangential velocity to keep the satellite in circular orbit at that position. So you won't be given this equation directly. You can derive this equation by setting, again, the force of gravity equal to the centripetal force and analyzing the centripetal force on the satellite itself, where this is the mass of the satellite. But it's an interesting takeaway and one you should store in your notes for use later. Okay, so let's apply this to solve for the necessary tangential velocity a satellite must have to maintain an orbit of 420 kilometers above the Earth's surface. The International Space Station actually orbits at this distance from the Earth's surface, so we'll take a look and see what velocity that satellite would have to have, or does have, to keep doing what it does. In this case, I know the force of gravity, I've written out my equation, and the mass of the Earth and radius of the Earth are given. I'd encourage you to pause the video right now and see if you can solve this problem, deriving the same expression for the velocity of the satellite that we derived in the previous slide. Okay, I'll go ahead and show the derivation here once more. All right, now the challenging thing about this problem is calculating r, right? It's really easy to just plug in the radius of the Earth here for r, but that is not what r is, right? R is the distance between the center of the Earth and the satellite. So this distance right here, this radius, is given. So r, right, r is this entire thing. So we're going to need to add the radius of the Earth and this orbital distance right here, this right here, the distance from the Earth's surface. So this is going to be 420 kilometers in this case, right? So I'll write that out here. R is equal to the radius of the Earth, 6.38 times 10 to the 6th meters, plus 420 kilometers. Now, I'm going to convert kilometers to meters to make this simpler to solve. That'll be equal to, so 420 kilometers, right, is equal to 420,000 meters, right? There's 1,000 meters in a kilometer, but this is just equal to 4.2 times 10 to the power of 5 meters. I can also write that as 0.42 times 10 to the power of 6 meters, allowing me to add more easily. And that means that my r, or my distance between the center of the Earth and the satellite, is 6.82 times 10 to the power of 6 meters. I'll go ahead and plug the r value I've calculated, the mass of the Earth, and big G into the tangential velocity equation now. Doing so gives me a necessary tangential velocity of 7,650 meters per second to keep this satellite in circular orbit. This concludes our series of videos on universal gravitation and orbits with satellites. Please take a look at Canvas for additional practice problems to further apply your skills.